Okay, for this screencast, what we're going to do is we're actually going to convert this to the Laplace domain and then simulate it using the transfer function. So let's just say you want to do a transfer function by itself. So let's take, oh crap, my battery's low. Hopefully I get through this video. So I'm going to take this system of equations here, Control C, and I'm going to go over here and actually what I'm going to do is I'm actually going to get rid of this 3 cosine t, and I'm just going to put f here, and that's going to be my input. And so if I convert this to the Laplace domain, I'm going to get big X s squared plus 5s plus 3 equals f. And so my transfer function g is 1 over s squared plus 5s plus 3. Okay, so basically I want to make this transfer function in Python. And so what I'm going to do is I'm going to import the control toolbox as C, and I'm going to say my system is c.transfer function, and I'm going to give it the coefficients of the numerator, and then I'm going to give it the coefficients of the denominator. And I'm going to call this transfer function example.py, and I'm going to print system just to make sure it's working right. And there it is. And then I am going to do a step response, and I think I need to open my other transfer function example just to make sure I have this right. So yeah, you need to actually give it how long you want to simulate it for. So I'm going to say t out is np.linspace 0 to 4, so that's still only going to simulate for 4 seconds. But that also means that I need to import numpy as np. And then basically I'm going to say, what did it say over there? It was t out, t out, y out. So I'm going to say t out, y out is c dot step, was it step response? Do we want to do a step response? Yeah, sure. Can we do impulse response? Let's just do impulse response. Impulse response of g, or sorry, I'm going to do my system and then t out. Is that good? That worked. Okay, so then I'm going to do import matplotlib.pyplot as plt, plt.plot t out y out, and there we go. Plt.close, come on. Plt.show. You don't show it, you won't see it. Okay, so there's the impulse response. So how do I know this is right? Let's go back and change this to step response so we can actually simulate this in using the ODE int. Okay, so here's a step response for 4 seconds. Let's do like 10 seconds, like that. Okay, so there's a step response of this system, of this transfer function. How do I know this is right? Let's copy all of this. Let's just get import control as C. Go back to the ODE int example. And throw that in there. Let's change the input to just 1.0, well, just to f, and let's say f is 1.0 because that's a step response. Okay, and then go back over to transfer function example. I'm going to make my system, and I'm going to get my system. So down here, when I plot this, I'm also going to create my transfer function. And I already have t out, so I don't need to do that again. And then I'm going to do plt.plot t out comma y out, except I'm going to do color equals green. And I'm going to do label control toolbox like this. And then up here, this is going to be label scipy toolbox. And what do I get? 2 graphs. Oh, I forgot about the legend. Plt.legend. And so they're right on top of each other, which means I did it right. So I have simulated a transfer function using the control system toolbox, and I've also simulated the system with ODE, the ODE int package. Okay. So the only other thing is, what if you have, instead of doing transfer function, what if you want to do zeros, poles, and gains like that? So how do you do that? So let me look that up real quick, and I'll come back. Okay, so in order to use the zero pole gain function, you need to use SciPy again, and so you want to do import SciPy.signal as S, and then you want to do s.zpk to transfer function. So there, I'm going to say no zeros, poles at -3 and -5, 1, and then what it does is it gives you the numerator and the denominator. So then you just do C, which is the control system toolbox, dot transfer function ND, and that'll give you system 2, and so here it is. And so the poles of this transfer function here are -3 and -5, and so if I do a step response of this guy, I should just get this is sys2, and if I do this should be y out 2, and if I do plt.figure to give me a new figure, plt.plot t out y out 2, I should get an overdamped response, and I do. Here's my figure 2 overdamped. This one's probably overdamped too. I wonder what the roots are. So if I go and click, so if I say here's D1, and I say D1 is 1, 3, 5, and I say np.roots of D1, I do print, what do I get? So, oh, they're actually imaginary. So why doesn't this one oscillate? Oh, wait, what? What? Why was it critically damped before? That's odd. 1, 3, and 5, right? We go back to OD int. 1, 3. Oh, it's 1, 5, 3. Why didn't you guys catch that? There we go. Okay, that's critically damped. Or overdamped, sorry. -4 and, okay. Yeah, that makes more sense. Okay, yeah, so there's my response that I got before. That's weird. Okay, so both of the systems that I created here were overdamped. But if we want, let's make a crazy oscillatory mode. Let's just do like -2J and 2J. So that second one should just oscillate forever. Yeah, and it does. Cool. So because we have poles at the imaginary axis. Okay, I think I've beat this one to a dead horse. So sorry, that's a terrible analogy. No harm on horses. I think I've exhausted the lecture here. So I'm going to stop. Any questions, post in the comments, and I'll try and help you out. Good luck.